So to elaborate on some of those limitations, what are some of the current limitations in the materials that we use in electronics? In particular, the materials issues with respect to connectivity issues that you had kind of alluded to in that last response there.
The major limitations with miniaturized electronics that we have these days is essentially the interfaces. It is not the material per se, it is not the device per se, but the interface between the other component that it's making, that becomes the limitation. It's a solder, right? Even if you're talking about simple solder and putting in so much voltage, there's so much current passing through it. What do you expect? You expect there's going to be some atomic diffusion happen. Metals will be diffusing from one end to the other. What would that happen? It will deplete the amount of conductivity that you're looking at. It will generate a lot more thermal problems into it. So limitations currently that I see is mostly for the interfaces. The other thing is the processing of these material into thin films. We're talking about copper, standard material, standard interconnection, highly conductive in nature, doesn't corrode as much, and it is cost effective. It will do what it needs to do. Problem is now when your IC is gone down to a few millimeters, your interconnection is going to go down to micron sized. When you have a micron-sized copper, you want it to stand only a few micron away from another line of copper. How do you actually process it so that it doesn't have processing issues? I don't want one line of copper to be broader than the other line of copper. They need to be at the same height, at the same thickness, same pitch, because it's going to create all other electrical concerns. There is something called as capacitance or capacitive coupling that will start happening between these copper lines. When we don't want that to happen, it will do a lot of crosstalk, which will again further deplete the properties. So processing and interface, two major limitations in electronics these days is what I would say.
So let's take that back to a higher level. Is interface and processing, is that the reason that if you leave your phone in a car on a hot day, it overheats and you can't use it until it cools down? Or like if you drop your phone in the water, it shorts the circuit. Is processing and interface the causes behind that, or is it something else?
Just the manual or mechanical use of material. The first thing to fail are the interconnections, the interfaces. It's still those when you drop your phone, other than the screen that you see, the electronics inside, the first thing will break will be the solder. It's not as protected. It's the interface again. You are trying to marry two different materials. You want to have them a strong metallurgical bond, and you want to run and rerun with certain voltage, temperatures, and so much changes. Just the amount of shear where the material is going to go through, they are the most prone to failures. And if you're asking me the inconveniences, you see how our electronics these days, they work fantastic when you buy them for the first 2 years. Third year onwards, they have an upgrade and yours starts heating up. I won't call it as an inconvenience, but I wish that material scientists work towards bringing the shelf life of these materials and these electronics longer. Because it's not just, oh, my computer is heating up and I need to change the fan, or I'll go and buy a new electronic. It's not just the inconvenience of the use, but also long-term disadvantages that we're going to all end up with. It's going to end up in the landfill. We don't know how to, so much electronic wastes that we're generating. So inconveniences are more than just consumer related. And a lot of this has to come with much stronger interconnections. When I say interconnection, I mean the interfaces between materials.
Do you think that it's money related in terms of why why our phones, are only great for 2 years? Because then, Apple would want us to upgrade to the next phone and pay money there. Or do you think it actually is materials related?
It's actually a combination of both. Obviously, consumerism is what is driving it. But of course, they are limited by the material, the way they are being processed. Everybody wants to stream a very big video while attending a class, online virtual class, and also talk to their family and friends on the phone, all three things at the same time. We need the power of my computer, processing power, to be over the roof. So with that demand, so consumers are driving it, and companies would take it and say, well, in next 2 years, I'll come and bring you with something. Of course, the infrastructure that I have will only support that level of advancement. So it is a combination of both.
So to further dig into this cost side of electronics and to how that plays into the material science, so what are some of the modern cost pressures on electronics? So for example, you had mentioned that gold is one of the materials used for interconnectivity of these electronics, but gold, as we all know, is not a particularly cheap material to come by. So is there research being done into creating cheaper alternatives to some of the more costly materials that have to be used today in building electronics?
Because you're talking particularly about gold, let me talk about it. So we'll start with why gold? Why is gold used in the first place? Because we know it is extremely high in conductivity. Electrical conductivity is high. It won't corrode easily. Its surface finishes are excellent. And it is fairly easy to come by, right? It may be expensive. It's humans who have given it a certain level of importance to the metal itself, right? But among property-wise, you can't beat its electrical properties, their thermal conductivity, and the corrosion resistance. Because of these properties, that's why it's being used. And honestly, it only is taking maybe a very minuscule amount of gold that goes in it. Where does it go? It is used in surface finish of a PCB board. It is also used in wire bonding material because it will solder very well. It diffuses very easily into metals and forms a good metallurgical bond. So it's, if you desire a cost reduction design and you don't mind a slight deterioration in the performance of a material, sure, there are other alternatives for gold. For example, there is something called ENIG, which is electroless nickel gold. And what it does is it is an electrochemical process where you make a very thin amount of gold, and then it's in combination with nickel in it. That makes a good bond of interconnection between the two, sites for soldering. Nickel actually gives you the wear resistance, and gold gives its electrical conductivity. And then the diffusion barrier between the two areas was given by nickel. So ENIG is very commonly used. It uses a small amount of gold. If you want to replace it, the other alternative these days are organic soldering. And they are called as OSPs, which is organic solderability preservative. And they form a very thin organic coating on the base of the metals. Usually it's copper. The material does not give very long shelf life, but it's definitely cheaper than gold. Okay, so that's one alternative. The other one is also called as HASL, which is short form for hot air solder leveling. And what it creates is a layer of tin lead, tin silver, or copper. And it isn't as expensive as gold, but it can result in thicker solder intermetallic, which decreases the solder life. So there are alternatives to gold that are available already. But it comes with a slightly, which is very minuscule, honestly, performance deterioration. And many of the consumers won't even see this. In total honesty, material cost is very, very minimum. If you start with the wafer, if you have to guess, how many steps do you think the wafer will go through from being a wafer and to get to a chip that will sit on your laptop? How many steps? Take a guess.
5?
10.
There are about 500 steps.
Oh.
We were not close.
Okay.
I was closer though.
Closer, yes.
So what you're saying though is that materials cost compared to processing costs in this industry is just totally in a different range.
That's right.
Yeah.
You're using 10 nanometer of gold in ENIG of solder and the entire wafer. It's going to be too little for the other 500 steps that it's going to go through.
Fair enough.
We were so far off.